All right, in the last chapter, we introduced Newton's laws of motion and we looked at some basic examples of Newton's second law. Now we're going to continue looking at Newton's second law and talk about some other forces that are included in the second law. One of these, of course, is friction. So frictional forces are unavoidable in our daily lives. If we weren't able to control them somewhat, then they would stop every moving object and bring to halt every rotating shaft. So frictional forces are unavoidable. About 20% of the gasoline we use in our cars is needed to overcome friction. And it can be even higher than that in things like trucks, for example. But if there were no friction, our cars wouldn't move at all. You couldn't ride a bicycle. You couldn't even walk. Nails and screws would be useless. They would just fall out. So you couldn't even build a car. All the bolts that hold parts together would just fall apart. You couldn't even weave cloth. So a cloth, the threads in a cloth would just fall apart. Knots would come untied. So friction is also necessary as well. So we do need some friction. So we're going to look at friction between dry solid surfaces that are either stationary or moving across each other at slow speeds. So for example, if I set a book on our table and I give it a shove so that it goes sliding across the table, we see that it will slow down and come to a stop. Thus, it has an acceleration, and there must be some force acting on it to produce that acceleration to make it come to a stop. If I push a book across a table at a constant speed, I'm applying a force, but at a constant speed there's no acceleration. So the net force on the book must be zero. So there must be an opposing force. If I push on a heavy desk that's sitting on the floor and the desk doesn't move, there must be an opposing force to my push that keeps it from moving. So these are examples of friction. So when I apply a horizontal force to a heavy desk sitting on the floor and the desk does not move, that means there is an opposing force that acts against my push. This is the friction between the desk and the floor. And when the object is not moving, we call this force static friction. And for the symbol, we use a lowercase f with an s subscript for the static friction. That static frictional force only exists when I push on the desk. When I stop pushing on the desk, that frictional force goes away. If I only push a little bit, then that static friction is just equal and opposite to my push. And so it's only going to be as large as what I push. If I push harder and the desk still doesn't move, then that frictional force, static friction, increases. So it's always equal to what I push. And when I stop pushing, well then that static friction force is also zero. Now, what if I push hard enough for the desk to slide across the floor? Then when we have the feet sliding on the floor, that is called kinetic friction, and we use a lowercase f with a k subscript to indicate kinetic friction. So F sub s is static friction and F sub k is the kinetic friction. So in the figure on the left, I have a block at rest on a table with the weight downward and the normal force of the table pushing upward. And then I'm going to apply a force F to the right. I'm going to start with 0 and gradually increase that force F. So as that force F is increasing and the box has not moved yet, then we have a static frictional force to the left that exactly balances the applied force F. Okay, so eventually the applied force gets great enough that we overcome the static friction, and at that point the block will start to slide across the table and we will have kinetic friction. So while the block is at rest, the static frictional force exactly equals the applied force F. Now this is shown at the graph to the right. So the applied force F is on the horizontal axis and the frictional force is on the vertical axis. So as I increase the applied force F from 0, we see we have a straight diagonal line where the static friction exactly equals the applied force, but in the opposite direction. Once I reach the maximum value that static force can be, if I increase F beyond that point, the box breaks free from the static friction and slides across the table. In that case, the frictional force drops and then becomes approximately constant as the block slides across the table. So the kinetic friction then stays approximately constant as the box is sliding. But before we start moving, the static friction will always exactly equal the applied force because there's no motion horizontally, so those forces must be equal and opposite. So when I push on the box and it doesn't move, then the static frictional force is equal and opposite to my push, right? And if I push harder and harder, the static frictional force then gets larger and larger. But the magnitude of the static friction has a maximum value. If the horizontal component of my applied force exceeds the maximum value of the static frictional force, then the block will break free and then slide across the table. Now it becomes kinetic friction. So once it's sliding, it's kinetic friction. The maximum value of the static friction is given by the expression here. So F sub s maximum equals mu sub s times the normal force. So F sub n is the normal force. Mu sub s is called the coefficient of static friction. So notice that the coefficient of static friction is just a number. It does not have a unit associated with it. Right? Since we have to have force equals force, the coefficient of static friction is just a number. And it's determined experimentally. All right, so in general, the magnitude of the static friction is less than its maximum value. So we write the static frictional force, F sub s, is less than or equal to mu sub s times the normal force. This is because the static friction only exists when I push on the box and it doesn't move. And so it's only equal in magnitude to what I push. If I don't push, that static friction is 0. It's only going to be equal to what I push up into its maximum value. Now once the box is sliding across the table, then the opposing friction is called kinetic friction. The magnitude of the kinetic friction then stays approximately constant. And we can write that as F sub k equals mu sub k times the normal force, where mu sub k is the coefficient of kinetic friction. So in general, the coefficient of static friction will be greater than the coefficient of kinetic friction. And you can try this yourself. So get a smooth table and put your hand on the table and push down, and then push slightly to the side as well. So your hand force on the table has a downward component and a horizontal component. And then gradually increase the horizontal component until your hand breaks free and slides. So you notice that you have to push harder and harder horizontally, but then once your hand breaks free and starts to slide, you don't have to push as hard to keep it sliding. The same thing if you're trying to slide something across the floor or the table by pushing on it horizontally. You push harder and harder and harder until it breaks free, but once it breaks free, it's easier to keep it going than it was to get it started, right? So the static friction coefficient is generally going to be greater than the kinetic friction coefficient. And again, these are just pure numbers. They do not have any unit associated with them, and these numbers are determined experimentally. There is no theory that will tell you what this value is. All right, let's look at an example. We have a block lies on the floor. A, what is the magnitude of the frictional force on it from the floor? Part B, if a horizontal force of 5 newtons is now applied to the block, but the block doesn't move, what is the magnitude of the frictional force? Part C, if the maximum value of the static frictional force is 10 newtons, will the block move if the magnitude of the applied horizontal force is 8 newtons? D, if it is 12 newtons. And then E, what is the magnitude of the frictional force in part C? So we're going to answer these questions. All right, so if the box is just sitting on the floor and you're not pushing on it horizontally, well then there is no static frictional force. So since there's no applied horizontal force, the friction force is 0. All right, now what if the horizontal force of 5 newtons is now applied to the block and it doesn't move? Well, if I apply a horizontal force of 5 newtons and it doesn't move, well then the frictional force is going to be 5 newtons, so that the net force is 0. So the corresponding static frictional force is only going to be equal to what I push, so that the net force is 0. All right, so what about part C? If the maximum value of the static frictional force is 10 newtons, will the block move if I apply a horizontal force of 8 newtons? Well, since the applied force is less than the maximum static friction, the block still does not move, and the static friction will equal to the 8 newtons that I push. So the net force is 0. Now, what if I push with a force of 12 newtons? Okay, well, we're given that the maximum static friction is 10 newtons. So if I push with a force of 12 newtons, my applied force is greater than the maximum static friction, and now the box will move. And it will slide, and we no longer have static friction. At that point, we will have kinetic friction. And finally, the last question says, what is the magnitude of the frictional force in part C? Well, in part C, since I'm pushing with 8 newtons, and the block is not moving since we haven't reached the maximum static friction yet, the static friction will be equal to what I push, and so it will be 8 newtons. Alright, so in the next video, we'll work out some example problems that involve both static and kinetic friction. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel, and please subscribe. I hope you find my videos useful.